Suppose I give you a 2 by 2 matrix like this one, and then I say, describe this matrix. Well, then you could reply by saying, well, this is a matrix with entries 0, -3, 2, 5, and it's a 2 by 2 matrix. Okay, that's not so helpful though. I don't really care about exactly what the entries are, so let me clarify. What does A do? So when I have a 2 by 2 matrix, I can apply it to vectors with 2 entries, and it'll give me out vectors with 2 entries. And how are the inputs related to the outputs? Or how are the outputs related to the inputs? So that's really what I mean by describe A. I don't really just want you to tell me what the numbers are. So can you describe what A does? So let's say I want a one-sentence description of what A does. What does this matrix do to vectors? Well, I guess you could do something like this. You could respond by saying, well, given a vector, A will take the second component of that vector, multiply it by -3, and make that the first component of the new vector, and then it will take the first component of the old vector, multiply that by 2, and add that to the second component of the old vector multiplied by 5, and then add the results together, and that will be the second component of the new vector. That would be perfectly accurate, and with the correct punctuation, maybe that is a one-sentence description. But does that really tell you, does that really give you a feel for what A is doing? It's perfectly accurate, but it's sort of not, it's not a compact enough description that we can make much use of it. Basically, that description is giving way too many details. And the amount of detail is obscuring sort of what's really going on. Okay, well, we can just look at what it does. So we've got 0, -3, 2, 5. Then I've typed that here into Inkscape, where I've drawn a smiley face. And I've typed in for this transformation that I will apply 0, -3, 2, 5. And I select my face. And you can see 0, 0 here. So I've put the face at sort of the corner of the page here, so that the middle of the face is the origin. Then apply this. Oh, okay. Interesting. So it apparently this matrix does that, whatever you're seeing there on the screen. So let me look at that again. Maybe I could describe what A does by saying it sort of smears out, maybe with a little bit of a rotation, and smears things out along this line? Okay, but that's a little bit too vague, right? Well, let's look at an example where you can totally describe what's going on. How about this matrix, 2, 0, 0, 3? Same question. What is this matrix? Or rather, what does it do? What does it do to vectors? This one's actually pretty easy, right? When you apply this to a vector xy, you just get 2x, 3y. That's because it's diagonal. Diagonal matrices are pretty easy to describe. So you could describe this matrix as one that doubles the first coordinate and triples the second coordinate of any vector you give it. That's a nice, short, compact description, and we can visualize it very easily. So if I go here and I type in 2, 0, 0, 3, and apply that, there we go. So you see it got a little bit distorted, but in a way that we totally understand. Horizontally, it got doubled, and vertically, it got tripled. So now it's kind of tall. So I could just draw some arrows or put some lines here that indicate in which directions the different scalings are happening. So when I apply this matrix to 0, 0, 3, I get a doubling along the purple direction here. And so I put a 2, scale factor of 2. Then I get a tripling along the green direction, scale factor of 3. So this height from the middle of the face to the top becomes 3 times as high from here to there. And from the middle of the face to the right here becomes 2 times, so that just gets doubled. And things are pretty simple when you're looking along those directions. Now even here with this diagonal matrix, things are not that simple if you look along directions that are not along the coordinate axes. For example, let me put this dot here where the eye is, and then let's track where the eye goes when I move things around. So 2003, it's tripled vertically and doubled horizontally, and now the eye has gone over here. Okay, this is not that accurate. It looks like it might just be getting scaled up. That's because my drawing is not so accurate, but I promise it's not just getting scaled up. Something kind of different is happening. If I draw a line here, it's not going to go through the origin. So yeah, my point is if you follow around points that are not along the coordinate axes, then the behavior of the result of applying A might look a little bit complicated, but because we can just focus in on the coordinate axes, we have this really easy to describe thing going on. Triple along one direction, double along the other direction. And then everything else that isn't so simple, we just let it do what it must do in order for the transformation to remain a linear transformation. Okay, so diagonal matrices are easy to describe. You just give the two directions in which things are getting scaled, purely scaled, and then you say what are the scale factors. So here A scales things in the horizontal direction by a factor of 2, and it scales things in the vertical direction by a factor of 3. And just knowing that, that's sort of enough to tell you what happens to everything else, even those things that don't get scaled, like things that are not along these two directions. So let's go back to our question here about 0, negative 3, 2, 5, or just any random 2 by 2 matrix. What does it do? Maybe we can find some special directions where you just get scaling behavior. So when I apply this transformation, it looks pretty weird. Definitely these directions are not directions along which scaling is happening, right? Like if I just apply this, look what happened to the top of the head. It got moved to way over there somewhere, right? So it didn't just get scaled up along the vertical line. So this vertical line is meaningless. And similarly, the side of the head is not just getting scaled. These lines are meaningless. For this particular matrix, 0, negative 3, 2, 5, those directions are just not important directions to focus on, but there might still be important directions. Those important directions would be called eigenvectors. So eigenvectors will be, for a particular matrix, so if you have a particular matrix, then eigenvectors will be directions along which the behavior of the matrix is simply to scale vectors along that line. Just like when we were looking at this one, if you just look straight in the horizontal or vertical directions, the behavior of the matrix is just to scale along those directions. And you remember each one of these special directions along which you were getting scaling behavior, there was a number associated with it, right? A scale factor. So that scale factor is going to be called an eigenvalue. So like here, if I'm just doing the matrix 2, 0, 0, 2, it's just scaling along this direction and scaling along that direction. The scale factor here is 2. That's the eigenvalue for the eigenvector that points along the purple line. And the eigenvalue is 3. The scale factor is 3 for the eigenvector pointing up here. All right, so if you want to describe what a matrix is doing, if you want to understand in sort of a compact way or get at the essence of what a matrix is doing, then you want to know its eigenvectors and eigenvalues. In other words, you would like to know what are the directions, what are the special directions in the plane or whatever, in which the behavior of the matrix along those directions is simply to scale. Those directions are eigenvectors. And you also want to know what are the scale factors along those directions. Those are eigenvalues. So if A applied to a certain vector, let's call it V, ends up just being a scalar multiple of that vector, like a scalar lambda times V, then that's the eigenvector eigenvalue situation. So when this happens, then we call v an eigenvector for A, and lambda the eigenvalue associated to v. And we will require that v not be 0 here. So when this happens with v non-zero, then v is an eigenvector for A with eigenvalue lambda. So matrices have eigenvectors, and then matrices along with eigenvectors have eigenvalues. Now the whole point of an eigenvector is that it's a special direction, right? It's a direction in which the matrix acts by scaling. So this is why we don't really want 0 as an eigenvector. Every matrix has the property that if you apply it to 0, then you get a scalar multiple of 0, right? Every scalar multiple of 0 is 0 anyway. So 0 is just not an interesting one and not helpful. It's not specifying any direction. So if I were to go to my smiley face here and try to draw the 0 vector, it would just be a dot here at the origin. It would not provide me with a direction in which something interesting is happening. So by definition, 0 is just not something we allow as an eigenvector. Another thing to notice is that eigenvectors really are just directions. We only care about the direction the vector is pointing in. It doesn't really matter how you scale that vector. So if you double v, so let's say I come up with an eigenvector v for the matrix A. If I now double v, or multiply by -1, flip it around even, that's still going to be an eigenvector with the same eigenvalue. So I can just pull out the 2 like this, and then be like, well, that's lambda v, since v was an eigenvector with eigenvalue lambda. And then I can put the 2 back inside. So A applied to 2v, if AV is lambda v, then A2v is lambda 2v. So if v was an eigenvector for A with eigenvalue lambda, then 2v is an eigenvector for A with eigenvalue lambda also. So really, when you have an eigenvector, don't just think one vector. It's really the line along that vector is just a whole line of eigenvectors with the same eigenvalue. So like here in the diagonal situation, when we use the matrix 2, 0, 0, 3, the diagonal matrix, it doesn't really matter how long I make this purple line, right? What matters is that it's the horizontal direction that is the sort of eigen direction, I guess you could call them eigen directions, for the eigenvalue 2. So eigenvectors are really eigen directions. And I can move this endpoint here around. I can make it -16. That's just as good a description of the overall horizontal direction. Or I can make this like shorter. It doesn't really matter. Okay, so a matrix has some special directions. It can, at least. So a matrix can have some special directions in which it operates simply by scaling. Those directions, you could call them Eigen Directions, but a good way to describe directions is by giving a non-zero vector, right? Zero vector doesn't give you any direction. Giving a non-zero vector specifies a direction. It also gives you maybe a little bit too much information, right? You could double the vector and that would specify the same direction, but whatever. And then the scale factor by which your matrix scales things along that direction, that's the eigenvalue. So let's try to get at why in the diagonal matrix situation, why was this so useful for describing what the matrix does? How did this actually make things so easy? Well, here the eigenvectors were 1, 0 and 0, 1, right? Or 2, 0 and 0, 17, however you want to describe it, but something horizontal and something vertical. So these were the eigenvectors for A, and the associated eigenvalues were so along 1, 0 the eigenvalue was 2, and along 0, 1 the eigenvalue was 3. So this is one eigenvector eigenvalue pair for this matrix, Here's another eigenvector eigenvalue pair for this matrix. What makes it so easy to describe the behavior of the matrix in these terms becomes apparent when you write vectors as linear combinations of these two eigenvectors. So if I just write vectors like, let's say I want to know what is A of xy, if I want to know this and let's say I ignore this grid of numbers here and I only focus on the eigenvalue, eigenvector information, so only use the fact that these two are eigenvectors and these two are eigenvalues, then what I can do is write this vector as a linear combination of 1, 0 and 0, 1. Then what will this be? Well, A is linear. That's the whole point of linear algebra, right? That's why we even care about the action of matrices on vectors, is because it's linear. So what that means, linear, means it distributes like this. And then A on 1, 0, well, 1, 0 is an eigenvector with eigenvalue 2. That means A on 1, 0 is 2 times 1, 0. And 0, 1 is an eigenvector with eigenvalue 3. That means A on 0, 1 is 3 times 0, 1. So while A might be some kind of complicated square matrix, A on these specific vectors is just numbers times these vectors. So A just became a 2 here and it just became a 3 here. That's what's so great about eigenvectors. And maybe I could repackage things like this. So 2x, 1, 0, plus 3y, 0, 1. And then from beginning to end, from start to end, look at what happened to the coefficients. So my input vector is here, and my output vector is here. And when I write my input vector as a linear combination of 1, 0, 0, 1, applying A had the following effect. It took the first coefficient and doubled it, and it took the second coefficient and tripled it. And that's what we really mean when we say A stretches the horizontal direction, this is the horizontal direction, by a factor of 2. It stretches the vertical direction, this is the vertical direction, 0, 1, by a factor of 3. And it treats everything else in the way that it must treat it in order to be a linear transformation. So you see, when you decompose vectors like this as linear combinations of 1, 0, and 0, 1, the behavior of A looks pretty simple. But that's not always going to work for 1, 0, and 0, 1. That worked here because 1, 0, and 0, 1 are eigenvectors for this particular transformation, for A. But what if we go back to the original question about this random-looking matrix, 0, -3, 2, 5? What does A do? If I just go and blindly try to use 1, 0, 0, 1 as a way of breaking down vectors, and then go like, okay, well, if I apply A to this this kind of breakdown, then what happens to this coefficient, what happens to that coefficient? Well, then you get something that you cannot really work with. It definitely does not have that nice, easy interpretation, right? Like, it looks like the coefficient of this one just became -3 times the coefficient of that one, so that one ended up there after applying A and got multiplied by -3, and then both of these end up getting combined in some way to make the second coefficient here. That is not the nice, simple kind of description we're going for, where we want sort of independent we want the action of A to be independent, operating independently on this component and this component. So here, this just gets one thing done to it, it gets doubled. This gets one thing done to it, it gets tripled. Here, what A does to this, what happens to this coefficient when you apply A to the vector is something that involves both of these coefficients. It's similar to this problem of coupled systems of differential equations. You're getting this mixing, right? And then here, this, what happens to the second coefficient here, this is a formula that depends on both of the previous coefficients. So this description is no good. Although it's accurate, it's just not what we want. It's not the best description we can get. And the reason it's not good is because I just chose these vectors 1, 0, and 0, 1 for absolutely no reason. Why am I using these vectors? These are not eigenvectors for this matrix. They were eigenvectors for this diagonal matrix, but what I should do for this matrix is actually use eigenvectors, right? So now we'd like to find the eigenvectors and eigenvalues for this matrix. It was easy for this one since it's already diagonal to begin with, and so 1, 0, 0, 1 did it. But here it's going to be more complicated. I'm actually going to skip to the answer and then show you in the next video how to actually find the eigenvectors and eigenvalues. So when you do this, when you try to solve this, so basically what we have to do is solve this, right? There's two unknown vectors, there's one unknown vector, v, and one unknown scalar, and you're trying to solve this for the unknown vector and unknown scalar. When you solve this, that's called solving the eigenvalue problem for the matrix. So you could call this the eigenvalue problem for A. So that'll be in the next video, but here's the answer. So I actually pulled this matrix straight from your homework, from homework problem 1, so I'm just going to have it tell me what the answers are and pick them right off of here. Okay, so I've got eigenvalues 2 and 3 and eigenvectors these. Okay, so here are my two eigenvector-eigenvalue pairs, which I just got by cheating and skipping to the answer. And I just want you to see how these are useful for describing the matrix. So let's suppose I give you vectors, instead of giving you vectors as a linear combination of 1, 0, 0, 1, I give them as a linear combination of these two vectors, negative 3, 2. So let's say x times negative 3, 2, and then y times 1, negative 1. Then what happens? So A is linear, so it distributes like that. And then A on this eigenvector is going to be eigenvalue times the eigenvector, right? So 2 times this eigenvector. That's the whole point of it being an eigenvector. And then this is an eigenvector with eigenvalue 3, so we just get 3. And look at that. We now have this nice sort of decoupled, simple description of how A operates on these coefficients, or how A operates on this vector, and how these coefficients change when you apply A. So the first coefficient just got doubled. So from here, this just got doubled. The second coefficient just got tripled. That's it. That's what A does. So as long as you write out your vectors as a linear combination of eigenvectors to begin with, you can see exactly what A does to the components. So totally decoupled, right? So here's my smiley face again, and I've got the same matrix in 0, negative 3, 2, 5, this one, whose eigenvectors and eigenvalues we're exploring. But this time I've put the eigenvectors, these special directions, down for this matrix. So this green one, this is 1, negative 1. So that's 1 to the right, 1 down, and I don't have to make it half size 1, 1, negative 1. I can make it as long as I want. Right, 2, negative 2 would be just as good of an eigenvector for eigenvalue 3. So anything along that direction. And then negative 3, 2, that's negative 3 over 2 up, or anything along that line. That would be an eigenvector with eigenvalue 2. So these labels here are the eigenvalues. And now when I apply the transformation 0, negative 3, 2, 5 to this matrix, to this smiley face, then I should get that things are stretching by a factor of 2 along this line and stretching by a factor of 3 along that line. And it's kind of hard to see, right? It's hard to see that that's what happened. But remember, we're just, it's only the vectors that are along the Eigen Directions that actually have this simple scaling behavior. Everybody anywhere else, everybody in between, is just going to get moved around in some complicated way that sort of that you can only really get at by decomposing vectors as linear combinations of the eigenvectors, which you can do visually, but we're not doing such a good job of doing that here. So it's really only the vectors that are along these lines that you can see they're just stretching. So I don't know, maybe here's a prominent point along this line. This portion of the eyeball here is sort of on the purple line, right? So focus on the distance between this left eye and the origin. Now apply this. That got doubled. So it used to be there, it moved out to there. You see? Maybe to make things easier, what I could do actually is move both of the eyes. How about I move both of the eyes so that they're on the eigenvectors? Starting to look kind of scary. So when you do this, you could call this an eigen smiley. So this is an eigen smiley. It has its eyes aligned along the eigenvectors when you center its face on the origin. Then now apply the transformation. So what should happen is this eye should should just double its distance from the origin. The origin is there. So this eye should double its distance that way. This eyeball should triple its distance. And you can see the eyes stayed along the lines. That one got moved out to there. And this one gets moved out to there, tripled its distance. And everybody else just has to get moved and stretched in some way that keeps everything linear. So let's go back to the question at the beginning of this video. What does this matrix do? We asked it for different matrices, this random looking one that I just pulled from your homework and this diagonal one. The diagonal one, it's easy to answer. What does this matrix do? Well, it doubles the first component, the horizontal component, and it triples the vertical component of any vector you give it. And now we have just as simple, almost as simple, of an answer for this matrix. What does this matrix do? Well, it doubles the -3, 2 component, and it triples the 1, -1 component of any vector you give it. So it's still just doubling one direction and tripling another direction. It's just that those directions are not just the horizontal and the vertical. You have to find out what they are. They're whatever these eigenvectors are.